Welcome back to Automata Theory. In this lecture we will look at context-sensitive grammars and linear-bounded automata. A grammar is said to be context-sensitive if for every rule x arrow y we have that the length of the left-hand side is less or equal to the length of the right-hand side and the left-hand side is non-empty. So basically, the right-hand side is not allowed to be shorter than the left-hand side. And this also means that during a derivation, the words can never get shorter. So why is this called context-sensitive? The idea is that for every context-sensitive grammar G1, we can construct a grammar G2 where the rules have this form. So we have some left context x, some right context y, and in the middle we have some variable a, and this variable a is replaced by v. The left context x and the right context y is preserved. So this looks a bit like a context-free rule. We replace a by v, but now this rule is applicable only inside a particular context, an x on the left and a y on the right. So this explains why these rules are called context sensitive. It's basically context-free rules inside a particular context. We say that language L is context sensitive if there exists a context sensitive grammar that generates the language except for the empty word. And we cannot expect the empty word to be produced because our words that we derive can never get shorter, so we cannot never derive the empty word from the starting variable. An example of a context-sensitive language is the language a to the n, b to the n, c to the n for n greater equal 0. This is a context-sensitive grammar for this language. Let's have a look. So from our starting variable s, we can generate just abc, this is the word for ns1, or we generate terminal a, variable a, terminal b, terminal c. Now, this variable a stands at the end of the a's in front. And from the variable a, we can generate more terminal letters a. And for each terminal letter a that we generate, we also generate a variable b. Now what's the task of the variable b? The variable b stands in front of the b's that we have produced. So the variable b now walks over the b's. It searches for the first c. As soon as it has found the first c, the b is rewritten to a b and a c. So the variable a generates terminal letters a, and it generates for every terminal letter a also a b, and this variable b will generate bc in between the letters b's and the letter c's. So let's have a look at an example derivation. So we want to derive the word aaa, BBB, CCC. We start from rewriting S to terminal letter A, variable A, terminal B, terminal C. To this word. Now we rewrite the variable A because we want to generate more terminal letters A. So we use this rule. We generate one terminal letter A, one variable B, one terminal letter A, one variable B. Now, the task of this b is to find the middle of the terminal letters b and c. So the b now starts walking over the b's. It has found the middle part. It stands in front of the c. So we use this rule. And now the b is replaced by bc. So this b becomes bc. Now we have two a's, two b's, and two c's. Now we want one more a and then we want to stop, so we now use this rule. We generate one terminal a, one variable b, one terminal a, one variable b, And again, the task of B is to walk over the B's and generate one BC in the middle of the B's and the C's. So the B, using this rule, walks over the first B, using this rule again, walks over the second B. Now it stands in the middle of the B's and C's. So we use this rule. The B stands in front of a C and we rewrite the B into BC. So now we have a word of 3 A's, 3 B's and 3 C's. And indeed, we can show that using this grammar, we can generate any word of this form. And indeed, these are the only terminal words that we can generate using this grammar. The class of automata corresponding to context-sensitive grammars are known as linear bounded automata. A linear bounded automaton, short LBA, is a non-deterministic Turing machine. So it's important, this is a non-deterministic Turing machine that does not use the blank symbol. So there's no blank symbol in our tape alphabet. Instead of the blank symbol, we have these special brackets that we put around the input word. And we require that if the Turing machine walks onto the left bracket, then it has to immediately walk to the right. And if the Turing machine walks onto the right bracket, it has to immediately walk to the left. So this means that these brackets bound the working area for our Turing machine. Our Turing machine cannot walk across these brackets. So effectively, the Turing machine can only work on the input word. It cannot leave the bounds of the input word. So this means that this Turing machine does not have an unlimited memory. The memory that it has is limited to the input word. So it only has a linear memory. So linear because it can still use a large tape alphabet. So it can be a constant factor of the input word, what it can use as a memory. The language of a linear bounded automaton is defined as follows. It's all words over the input alphabet, such that we have a computation that brings us to a final state. And this computation is now started in the starting state of the Turing machine with the input word put in brackets written on the tape. So we put these special brackets around the input word, and that is the tape content in which the Turing machine is started. So now the Turing machine stands on the left side of this input, so on the left bracket. So the first thing it will do, it has to move to the right onto the input word W. Now the computation is the same as in a usual non-deterministic Turing machine, and the only requirement is that we have a computation that brings us to a final state. And again, in this computation, due to these two conditions, the head can never move off the input word. Whenever we move onto the left bracket, we have to move back to the right. Whenever we move on the right bracket, we have to move back left. So we can only compute on the input word. Next, we will show that linear bounded automata are equally expressive as context-sensitive grammars. They both define the class of context-sensitive languages. We start with the direction from context-sensitive grammars to linear bounded automata. So we will show that for every context-sensitive grammar G, there exists a linear bounded automaton M, such that the language accepted by the linear bounded automaton is the same as the language generated by the grammar. The proof is really quite simple. If we want to know whether a word W can be derived by the grammar, we only need to consider words that have lengths up to the length of w. In the derivation of w, we never can have words that are longer than w itself because of the property of the rules of context-sensitive grammars. The right-hand side of such a rule is never shorter than the left-hand side. So this means if we apply such a rule, the words never get shorter. So now if we give w as an input to a linear bounded automaton, and our linear bounded automaton wants to determine whether this word is derivable by the grammar, then our linear bounded automaton is a non-deterministic Turing machine, so we can guess a derivation of w. We simply start from the starting variable and we start deriving, we start applying rules. And this works because in this derivation of w, we never have to consider words that are longer than w. So this means our linear bounded automaton never needs more space than just the input word itself. For every linear bounded automaton M, the language accepted by the automaton is context sensitive. This means there exists a context-sensitive grammar that generates this language, possibly except for the empty word. So how do we prove that this is the case? We have seen how we can translate Turing machines into unrestricted grammars in such a way that the language generated by the grammar is the same as the language accepted by the Turing machine. Now the same transformation we can also apply to linear bounded automata, because linear bounded automata are Turing machines. And if we then have a look at the grammar that we obtain, we actually find that all of the rules are context sensitive. So for all rules of the grammar that we have generated, the right-hand side is never shorter than the left-hand side, with one exception, and the only exception is this rule, which allows us to remove the blank symbol, replace it by the empty word. But linear bounded automata do not use the blank symbol. The read-write head never leaves the bounds of the input word. So therefore, we can actually drop this rule. We do not need blank symbols, and we can also drop these rules if we want. We don't need to, they are context sensitive. But since we cannot drop the blank symbol, we can also not really make use of these rules. So if we drop these rules, the grammar that we obtain is context sensitive. Now there's one slight hand-wavy part in this proof, and therefore it's called a proof sketch. Namely that from the starting variable, we will derive a word of this form. So we do not want to consider these brackets as extra letters. So we don't want to introduce extra variables v for these brackets. The reason is, if we would introduce them, because we want to in the end generate the word a1 up to an, that's our input word, then we would have to remove the brackets in the end. So we would have to make the word shorter again. That's not what we want. So we have to include these brackets into the subscripts of our variables. This is not difficult, but it's some extra work. And after having done this, then the grammar that we have is indeed a context-sensitive grammar, and this grammar generates the same language as our linear bounded automaton, possibly except for the empty word. Let's have a look at some basic properties of context-sensitive languages. The class of context-sensitive languages is closed under union, intersection, reversal, concatenation, cleaning star, complement, and difference. How do we prove this? For the union, the reversal, and the concatenation, we can basically take the same proofs as we've used before for context-free languages. The idea is just we take the union of the two grammars, so we have one grammar for L1 and one grammar for L2. We assume that they don't have variables in common, we take the union of the grammars, we add a fresh starting variable, and this fresh starting variable can rewrite to the starting variable of the grammar 1 and the starting variable of the grammar 2. Similar for the concatenation, but here the fresh starting variable can rewrite to S1, S2. For the reversal, we reverse all left and right hand sides of all the rules. So a rule x arrow y becomes x reverse arrow y reverse. For the cleaning star, we do it almost as before, but instead of having a rule s goes to lambda, this is not context sensitive, we have a rule s goes to s1. It's basically the same, but we don't produce the empty word. For the intersection, we may assume that we have linear bounded automata for L1 and L2, and we simply run them in sequence. So we take some input word, we first check whether our first automaton accepts the input word. If the first automaton accepts, then we run the second automaton on the same input word. If the second automaton also accepts, then we accept. Thereby we only accept if both accept, so we have an automaton that accepts the intersection of the two languages. For the difference, L1 minus L2, we can write this as L1 intersected with the complement of L2. The intersection preserves context-sensitive languages, so we only need to know that the complement also preserves context-sensitive languages. And this is actually a non-trivial proof, but really a marvelous proof. If you're interested in automata, it's worth looking into that. So what's the problem which makes it difficult? Linear bounded automata are non-deterministic Turing machines, and they accept an input word if there is some computation path that brings us to a final state. There may be many possible computations, because the computations can branch due to the non-determinism, and it's sufficient that one of them is accepting. Now, we want to make an automaton for the complement of the language. So basically, we want to ensure that there is no computation path that brings us to an accepting state. But in order to ensure this, we have to check all the possible computation paths of our non-deterministic machine. And this is possible, but it sounds like we need more space. We need to do some breadth-first search, so we need to possibly store all the different configurations that the Turing machine can be in on the tape. So how do we do this in a linear bounded automaton which doesn't have more space? We only have the input word to compute on. And the really ingenious idea is that if you want to know how many different configurations the Turing machine can be in after n+1 steps, you don't need to know what configurations the Turing machine can be in after n steps. You only need to know how many different configurations can it be in after n steps. So a single number is sufficient. You only need to know that after 20 steps it can be in 5 different configurations, and this information is sufficient to determine how many configurations can it be in after 21 steps. So we only need a single number, and we utilize the non-deterministic guessing feature of our Turing machines, and we can do this breadth-first search without using additional space. So I really suggest you to look into that if you're interested in automata. There's one famous open problem still for deterministic linear bounded automata. It's not known whether they are equally strong as non-deterministic linear bounded automata. The linear bounded automata that we have discussed are all non-deterministic, and the question that is still open is, are deterministic linear bounded automata equally strong? A priori, it sounds like this is not possible, because in order to simulate a non-deterministic machine with a deterministic automaton, we need to have more memory. We need to store all the possible configurations of the non-deterministic machine on our tape. But maybe some similar ingenious trick is possible to do this transformation. At present, it's still unknown, and it's one of the big open problems in this area. So let's have a look at how context-sensitive languages compare with recursive languages. Both are defined via Turing machines, but one is restricted in memory. So let's have a look how they relate to each other. Every context-sensitive language is recursive. So every context-sensitive language is accepted by a Turing machine that reaches a halting state for every input word. Let's start with a context-sensitive grammar G, and we're going to construct a Turing machine that accepts the language generated by G. Our Turing machine takes some input word W, and now we want to determine whether W is generated by the grammar. The crucial observation is, what we've already discussed before, that in a derivation using a context-sensitive grammar, the words can never get shorter. Therefore, we only need to consider words that have lengths at most the length of W. So our Turing machine can simply compute all the words derivable from the starting variable that have at most length W. So all the words U such that the length of U is at most the length of W. This set is finite and the Turing machine can compute it, and then all the Turing machine has to do is to check whether the word W is among this set. If it's in the set, W is derivable. If not, it's not derivable by the grammar. Our Turing machine accepts the same language as generated by the grammar, and it always reaches a halting state, so the language of the grammar G is recursive. Next, we are going to show that the class of recursive languages is strictly larger than the class of context-sensitive languages. So we are going to prove that there exist recursive languages that are not context-sensitive. We are going to consider the alphabet 01, so that's the alphabet of terminal symbols of our grammars, and also the input alphabet for our automata. First, note that we can denote context-sensitive grammars G by words over 01. So there exists a computable and injective function from context-sensitive grammars to words over 01. So how should you imagine this? Simply think about that we can denote context-sensitive grammars in ASCII text. You can simply write them down in ASCII text. And ASCII text is nothing else than a sequence of bits. So we have a notation for our grammars. One way to achieve this notation is given here. So the idea is that we denote the terminal letter 0 by 010. We denote the terminal letter 1 by 0110. So every code of a single symbol that we use always starts with a 0, then a certain number of ones, and then 0 again. So the terminal letter 0 corresponds to a single one, the terminal letter 1 to 2 ones, an arrow we use 3 ones, the semicolon for separating different rules of a grammar we use 4 ones, and we need to somehow denote variables. Let's assume that we have named the variables of our grammar as A1, A2 up to AN. Then we can denote AI by 0, and then I plus 4 ones, and then a 0 again. So A1 is denoted by 5 ones, A2 by 6 ones, and so on. Now the crucial point of having such a code is that we want to be able to check whether it's a valid code. So this means the image of this function h should be recursive. So we should have a parser that, given such a code, tells us whether this is a code of a valid grammar. And if we, for instance, take such a simple encoding, then this is of course no problem. We can easily write a parser that tells whether the code that we have is a valid grammar. Now, having such an encoding of context-sensitive grammars as words over 0, 1, we can define the following language L. We say that L consists of all codes of context-sensitive grammars, such that the code of the grammar is not in the language of the grammar itself. So the grammar G does not generate the code of itself. So we take all these codes that are not generated by the grammar itself into the language L. And this language L is recursive, because a Turing machine can take such a code, a word over 0 and 1 as input. We can run our parser that tells us whether this is a valid code of a grammar. And if it's a valid code of a grammar, then the Turing machine can check whether the code is derivable by the grammar denoted by the code. We've already discussed that a linear bounded automaton can check whether a certain word is derivable by a context-sensitive grammar. So our Turing machine can check whether the code of G that is given as input is derivable by the grammar denoted by the code. So now let's, for contradiction, assume that this language L would also be context-sensitive. So let's say that it's equal to the language of G0, where G0 is a context-sensitive grammar. Then we know the following. Namely, we know that the code of G0 is in the language L by this definition. So how is L defined? The code of a grammar is in the language, if and only if the code is not in the language of the grammar itself. So this is this by implication here. The code of G0 is in L, if and only if the code of G0 is not in the language of G0. And this is equivalent to, by this equality, here we assume that L is equal to the language of G0, so we can simply replace the language of G0 by L. So this is equivalent to the code of G0 not being in the language L. But now we have a contradiction, because we have that the code of G0 is in L, if and only if it's not in L. So our assumption must have been wrong. The language cannot be context sensitive.